Hi, everybody. Welcome to Module 4, Chapter 11, Transformations, Symmetries, and Tilings. I'm Melissa Pierce, and we're going to go ahead and jump into the lesson today. All right, here we go. So for question number 1, we are told that Ephraim and Devontae were asked to reflect the pattern block figure shown here on the left over the horizontal line through the center of the square. They rearranged the blocks to form the figure on the right. What type of rigid motion did Ephraim and Devontae use? And how can we clear up the misunderstanding they had about the problem? So first, let's look at what they did. They were given the figure on the left, and then they were asked to reflect it over a horizontal line going through the square. So what did they do wrong? Well, let's see. They started here, and then instead of reflecting it over the horizontal line, they did a rotation clockwise and wound up with this shape here. So let's go ahead and help Ephraim and Devontae see what happened. So let's start with the clear figure. So what we're going to do is we're going to fix what they did. So we are asked to reflect it over the horizontal line that I have drawn here through that square. So what would that shape look like at that point? It would look like this. The horizontal line would reflect right through the square, and then the figure would flip as so everything stayed the same angle. And what I mean by that is if you notice the triangles, they're all still pointing in that same direction because they're a reflection. Whereas if you look at Devontae and Ephraim's, they pointed different ways because they rotated it instead of doing the reflection. So that's what they did wrong, and that's how we could fix that problem. All right, let's move on to number 2. So for number 2, we are to identify these figures with the following symmetries if possible. So let's see. First, we're going to look at one line of symmetry. There are 4 of these figures that have one line of symmetry. Okay, so we have our lovely little hexagon there, 2 triangles, and a half circle. It's normally a little bit more perfect, but I hand drew that. So those all have one line of symmetry, and what that means is you can kind of look like a mirror reflection. If you draw one line through, and I've chosen to do a horizontal line, you could have done a vertical line as well. If you were to fold those in half, they would meet the other side perfectly. It's their mirror image. So let's go ahead and look at what would have rotational symmetry. So let's look at those figures again, and you can make your guesses now, but I'm going to go ahead and show you the first one that has rotational symmetry. So if you were to take this figure that looks kind of like a Tetris figure to me and rotate that 90 degrees, this is what you'd have. So if we were to rotate that another 90 degrees, totaling 180 degrees, we would have the original figure, which is what you need in rotational symmetry. There's one more figure that has just rotational symmetry, and it is this guy. Another Tetris-looking thing, but not quite. So let's rotate him 90 degrees, and then another 90 degrees, totaling 180, and we have the original figure, just like before. So let's look at the shapes on the top, and we are going to go and see which have both reflection and rotational symmetry. So look at those and take your guesses. There's only a couple we haven't used. We have this lovely rhombus/diamond shaped figure, and here I've shown a vertical line of symmetry, but you could have also shown a horizontal line of symmetry. And then here is the rotational symmetry, turning it at 90 degrees and then back to 180 degrees. And then here we have a rectangle. I've chosen a horizontal line of symmetry, but you could have also done a vertical line of symmetry. And then we have it turned at 90 degrees and again at 180 degrees. So those both have reflection and rotational symmetry. Let's move on into number 3 and meet Myra. So Myra cut out a rectangular pentagon, hexagon, and octagon, and it seems to her that they form a vertex figure, such as the one shown here. So we're going to respond to Myra and use some animations to demonstrate if she's correct or incorrect in saying that this is a vertex figure. So how could we find out if this is a vertex figure? So vertex figures, interior angles equal 360. So what that would mean is that the angles inside, meaning the green, the red, and the blue figure, would add together to be 360 degrees. Let's see if they do. So the pentagon, to find that, we would take the side, subtract 2, multiply that by 180, and divide by the sides, which is 5 in this case because we're working with the green pentagon. And we have 108 degrees. Let's look at our octagon, which has 8 sides, which is our red figure. We take the sides, 8 minus 2 times 180, divided by the sides again, which is 8, and we get 135 degrees. Now let's look at the blue figure, the hexagon. So we have the sides, which is 6, so 6 minus 2 times 180 divided by 6 equals 120 degrees. So is Myra correct? Let's find out. So let's add all those angles together. We find that unfortunately Myra miscalculated by 3 degrees. This is not a vertex figure because it does not equal 360. But let's show Myra how she can fix it, you guys. So here's what Myra can do. If she were to add a 3-degree gap, meaning that those shapes would no longer touch right on each other, that would mean we could subtract those 3 degrees from the 363 and give her a 360-degree vertex angle. And there you go, Myra. All right, so for number 4, we were going to use PowerPoint to draw a line M, which you can see here, and a point P that's not on the line. So after we did that, we construct an area centered at P that intersects the line in 2 points, Q and S. Next, we were to draw 2 arcs of equal radii centered at Q and S, labeling their intersect point as T. Finally, we were to construct the segment from P to T and let V equal the intersection with the line M. This figure is shown to the right, or to the left in my case. So once we've recreated the figure, we have some tasks we need to get done. So what I'm going to explain to you is why triangle QPT is congruent to triangle SPT, why angle QPT is congruent to angle SPT, why triangle QPV is congruent to triangle SPV, and why QVP is a right angle. So let's look at this, shall we? Let's go ahead and take a look at QPT and SPT, those triangles that I've outlined here in these different colors. So this is kind of like the angles. We're going to show why they're congruent. Well, if we look at PT in a different way, the way we've been looking at other things, such as problem 2, we can see that PT is semi-acting as a line of reflection. So if we were to fold that lovely figure in half vertically, it would meet perfectly, which means those triangles are exact. They are congruent. They are even because there would be no overlap or no access left if we folded that line over from P to T. So QPT, the angle, and angle SPT are congruent using that same logic. So let's look at QPT, that angle on top, and then we look at SPT, that other angle. Those folded together would be the same, so that means they're the same. In fact, they're congruent. So let's look at the smaller triangle, and we have QPV and triangle SPV. So we have that in yellow right up top. If we were to fold that over, that means that they are equal to each other. We could use that same line of reflection. Granted, we couldn't fold over Q and S because horizontally that doesn't work. Vertically, it does. Those angles are exactly the same. They are congruent. And that also kind of helps us explain why there is a right angle of QPV. That right triangle fits perfectly there. We could also say the same for PVS if we wanted to, as well as QVT and SVT are also right angles if you looked at it that way. All right, let's move on to number 5, shall we? So we have a regular pentagon, penta. Let's name it, shall we? So we have point P, E, N, T, and A. So let's look at penta. So if we were to insert a triangle PQR inside of penta and have P be the same for both shapes, which means they share the same vertex. So let's go ahead and give the Q and the R a place to live. So what we're going to do is we are going to form this figure, and then we are going to find the measurement of angle QON. So for this problem, we've already made our pentagon and our triangle. So now we need to find that NOQ measurement. So let's take a few steps to find this, shall we? So first, we're going to form our angle, the NOQ. But then we can also see that another triangle can be formed at QOP or QPO, whatever you want to call that. So we're going to go ahead and take that triangle and place it here, but then we're going to take it right back out and put it over here. So let's look at that triangle, shall we? We can tell that by looking at this triangle, a triangle measures at 180 degrees. Let's go ahead and give this triangle its measurements. So that larger obtuse angle is going to be 120, and the acute angles are going to be 30 degrees, totaling at 180. We don't need that just yet, but I put it there so you can remember we're going to use it later, so it's not going anywhere, you guys. Okay, so now let's take out penta, shall we? Why do we need it? Well, we need to find the interior angles of penta in order to find that pesky NOQ angle. So the interior angles are going to be 5x equals 360. After you divide both sides by 5 to isolate your x, you're going to find that x equals 72. Each of those angles in the pentagon, which there's 5 angles, equals 72. So why do we need that? Well, it's because our yellow triangle as well as NOQ are touching 2 points of that pentagon. So we're going to need 2 of those measurements. So let's go ahead and show that here. That aqua line is going to measure to be 144 because 72 plus 72 is 144. How's this going to help us? Well, we're just that much closer to finding NOQ. How? We're going to take 144 minus the 120 we used earlier to get 24 degrees, and that is what our angle of NOQ is. It is 24 degrees. All right, you guys, let's power through number 6, and we're going to meet Jenny. So by holding a ruler 2 feet in front of her eyes, as illustrated in this diagram, Jenny sees that the top and bottom points of the vertical cliff face line up with the marks separated by 1.5 on the ruler, and that's inches. Jenny is about a quarter mile from the cliff. What's the approximate height of a cliff? So let's go ahead and we're going to talk about triangles for a minute and state how the similarities between them can help us solve some problems. So we have 2 triangles here. I've made my red one outside of that just a little bit, but it really meets in the nose of that blue triangle. So we have 2 triangles. We're going to name this one ABC and our large one DEF. Let's look at that a little bit closer. We find that A is actually congruent to D, B is congruent to E, and C is congruent to F. That means that these triangles, while different sizes, actually have the same measure of angles, no matter what size they are. If you were to shrink the blue triangle down to the size of the red one, they would perfectly overlap, and the same goes for the red triangle. They're completely congruent. So, for example, line AB is congruent to line DE, line DF is congruent to line AC, and line FE is congruent to line CB. They're the same. So that's pretty neat to look at, you guys. So let's explain Jenny's problem. We're going to try to find that cliff height, okay? So here's Jenny again. How are we going to find that cliff height? Well, let's recall that 1 mile equals 5,280 feet. But Jenny's not standing exactly 1 mile, is she? It said that Jenny sees that the top and bottom points of the vertical cliff face up. So she is about a quarter mile from the cliff. So what does that mean? She's about a 1/4 of the mile out. So let's take the mile, divide it by 4 to get 1,320. We're not done yet though, because that's not the cliff height. That's just how far Jenny's standing from it. So that ruler, if you recall, is 1.5 inches. So we need to convert that into feet, which would be 0.125 feet. So let's do some math here. We have 2, which is the 2 feet, for Jenny's arm, is over the miles, 1,320, and then we have that ruler, which is 0.125 feet over cliff. But what's the cliff, you guys? Let's find out. So the cliff is going to be 0.125 multiplied by 1,320 over 2, and that's going to give us the cliff's height, which is 82.5 feet. And there we have that. I want to thank you all for watching my presentation, and I hope you all had a wonderful time, just like me, and I will see you next time, okay? Bye.